You know, the human heart is an absolute masterpiece of biological engineering. It's incredible. But what happens when it fails? Can we actually build a new one? For decades, that very question has been pushing the absolute limits of medicine and technology. So today, we're going to dive into the incredible challenge of replacing the human heart and uncover the surprising virtual tools that engineers are now using to design its future.
And the scale of this problem, it's just staggering. In the United States alone, nearly 400,000 people die every single year from causes related to heart failure. Think about that. That's like an entire major city's population, wiped out year after year. So for all those people who are desperately in need, the best possible solution, a heart transplant, is incredibly rare. For the last 2 decades, only about 2,500 donor hearts have been available each year in the US. It's a tiny, tiny fraction of what's actually needed.
So this brings us to the central question, the one that has driven this decades-long quest. How in the world do you bridge that enormous gap? How do you engineer a solution when nature just doesn't provide enough replacements? Well, the answer engineers came up with was, build one from scratch.
But here's the thing. Building a heart isn't just about building a pump. Oh no. It is one of the most demanding engineering challenges you can possibly imagine. The list of requirements is incredibly long and totally unforgiving.
I mean, just take a look at this list. A total artificial heart, or a TAH, it's got to be small enough to fit inside your chest, right? But it also has to be powerful enough to pump blood to your entire body. It can't damage your fragile blood cells or, and this is a huge one, cause blood clots. It has to be made of materials your body won't reject, it can't overheat, and oh yeah, it needs to run perfectly, 24/7 for at least 5 years. And maybe the toughest part of all? It has to perfectly balance the blood flow between the lungs and the rest of the body. A delicate dance your natural heart does with every single beat.
So, faced with this insane list of challenges, the pioneers in this field spent decades just trying to create a machine that could mimic the natural heart. And their journey, well, it was one of slow, really painstaking progress. The whole quest really kicked off back in 1957 with the first successful animal implant. Then, fast forward to 1969, the first TAH was used in a person, not as a permanent fix, but as a temporary bridge to keep them alive until a donor heart was found. Then, in 1982, came the famous Jarvik 7. It was implanted as a permanent replacement, and one patient survived for an incredible 620 days. But it actually took until 2004 for a version of that same device to become the first TAH officially approved by the FDA, and even then, just for that bridge to transplant use.
Now, the design philosophy behind the Jarvik 7, and really all these early artificial hearts, was based on a simple idea: just replicate nature. It used these 2 big pumps to create a pulse, pushing blood out into the body in rhythmic waves, kind of like a real heart. But all that mechanical complexity came at a cost. These devices were huge, and frankly, their durability was pretty limited.
But then, a radical question came up. What if that core assumption was just wrong? What if the human body didn't actually need a pulse to survive? This idea, it was a total game changer, and it would completely rewrite the future of artificial hearts. And you can see the shift right here. I mean, just look at the difference. On the left, you've got those bulky, complex, pulsatile pumps. And on the right, the next generation, these small, simple, continuous flow rotary pumps. The difference in size and complexity is just night and day.
So let's break it down. The old pulsatile pumps were super complex, and they topped out at about 2 years of durability. The new continuous flow pumps, incredibly simple, often just one moving part. And instead of a pulse, they provide this constant, steady stream of blood. That simplicity led to a massive leap in durability. We're talking devices lasting over 8 years.
And this, right here, was the revolutionary discovery. After decades of research, it turned out that mammals, including us humans, could live perfectly well without a pulse. It was a mind-blowing finding that just shattered all the old assumptions and blew the doors wide open for a new generation of smaller, simpler, and way more durable artificial hearts.
Okay, so building better hardware is one thing, but that's only half the battle. To really engineer a better heart, you first have to understand the unbelievably complex system it supports. You know, the thousands of miles of arteries and veins in our bodies. And this is where our story pivots, from physical machines to powerful virtual tools. I mean, just look at this thing. The circulatory system is a sprawling, 3-dimensional labyrinth. Figuring out how blood flows through this whole intricate web is absolutely critical if you want to design a device that works with the body, not against it. But trying to simulate this in 3D, the computing power needed is just immense.
So, engineers came up with a brilliant shortcut:
1D blood flow modeling. Honestly, the best way to think about it is like this. Imagine taking a super complex 3D map of a city and turning it into a simplified 1D subway map. Yeah, you lose some of the street-level detail, but you can figure out the most important things, like how to get from point A to point B and how long it takes incredibly fast. Same idea here, but with pressure and flow.
So, here's how it basically works. You start with the fundamental physics of how fluid moves. Then, instead of modeling every single point inside a blood vessel, you use math to reduce each vessel down to just a single line running down its center. Finally, you solve the equations for pressure and flow along this new network of lines. It's a really powerful simplification.
And the key benefit, the whole reason for doing this, is speed. As this quote points out, because it's so much simpler, it's computationally efficient. That means you can run massive simulations of the entire circulatory system, something that would be pretty much impossible with a full 3D model. And that incredible speed opens up a phenomenal new possibility, something almost out of science fiction: the ability to create a virtual patient, a complete, working digital model of a person's circulatory system that you can use for testing and analysis. So for example, we can model these incredibly delicate and vital structures, like the circle of Willis, which is the network of arteries that supplies blood to your brain. Using these models, researchers can simulate blood flow, see how it changes with disease, and even predict potential problems, like aneurysms or the effects of a stroke. And the applications are just vast. These virtual circulatory systems are used to study everything from high blood pressure to the narrowing of arteries. Doctors can use them to see the impact of plaque buildup and even plan surgeries. Think about it. They can test out placing a stent on the virtual model first to see exactly how it will affect blood flow in that specific patient. All right, so let's tie these two incredible stories together. On one hand, you have this decades-long, gritty quest to build a mechanical heart. And on the other, you have this cutting-edge development of virtual models of the human body. This is where it all converges. This is the crucial connection. To design the next breakthrough artificial heart, engineers don't just build prototypes in a workshop anymore. They build them inside these advanced computer simulations. They can test how a new pump design will interact with the entire body, how it responds to changes in blood pressure, how it performs under stress, all of it, before a single physical part is ever even made. And all of this is leading us to a really powerful idea, a future of truly personalized medicine. So let me leave you with this question. What if, before a major heart procedure, your doctor could test it first on your digital twin, a perfect virtual model of your unique circulatory system? That is the future this technology is building, one where engineering might just finally solve one of biology's greatest challenges.